All right, section 2.6, families of functions. We're going to go and talk about parent functions and then the transformations that allow us to go from that parent function and move our graphs all around the coordinate plane, whether it be a vertical change, a horizontal shift, a stretch, or a shrink. So here we have a parent function is the simplest form in a set of functions that form a family. A lot of you know that your parent functions are things like y equals x is your parent function for a linear function. You've got y equals x squared is your parabola parent function, and so on. Each function in the family is just a transformation of one of the parent functions. So as we add things to the equations, we're looking at shifting the graphs through some transformation. One type of transformation is a translation. A translation shifts the graph of the parent function horizontally, vertically, or both without changing its shape or orientation. And so here's something very important. For a positive constant k and a parent function f of x, when you have that function and you're adding or subtracting some constant to it, this is going to be a vertical translation. For a positive constant h, where in this case you are adding or subtracting that constant to the input or the x value, that is going to be a horizontal translation. And we'll look at this farther. If we look a little down below, this is showing some examples of vertical translations. And here we have horizontal translations. And we'll take a look at what this means. A lot of us have gone through school and we've graphed lines and we haven't really recognized how they're truly being affected by by the values in their equation. So this is what we're going to do. We're going to take a closer look at that. So here we have two functions, and it asks, how are the functions y equals x and y equals x minus 2 related? Okay, they want to know how the functions are related and how their graphs are related. So we can compare just the functions themselves without graphing this by looking at possibly a table of values here, so x and y, and so for x values, let's just say 1, 2, and 3. So these are your inputs. And then let's say let's make this y equals x, and then we'll have y equals x minus 2. And we're going to compare how the outputs look for each of these. So for y equals x, pretty easy. You've got 1, 2, 3. For y equals x minus 2, your outputs in this case would be -1, 0, and 1. So what we should notice for the two functions is that the y equals x minus 2 is the outputs are 2 less than the outputs for y equals x for the same inputs. And so then we can look at their graphs and see how they're related. So we'll go ahead and graph y equals x in red. Start at 0, 0. We'll apply our slope 1 over 1. And we'll do this till we have enough points. Then we're going to graph y equals x minus 2 in blue. Start at -2. Our slope is the same. And we should notice a difference here. We should notice that the graph of y equals x minus 2 is translated down 2 units. So because of the -2 at the end of the equation here, our graph for this particular function is translated down 2 units. All right, let's take a look at the next one. What is the graph of y equals x squared minus 1 translated up 5 units? You could use this table here, or you could just graph this, and we could use a table of values to graph y equals x squared minus 1. I'm just going to choose some values. You could also use a calculator. So I know if I'm plugging this in, let's say I'm using -2, -1, 0, 1, 2. So So this means we've got negative 2 squared is 4, 4 minus 1 is 3. This would be 0. This would be negative 1. This would be 0, and this is 3. Parabolas are symmetrical. So now we'll go ahead and graph the original function. Oops, wrong spot. There we go. So this is our parabola to start with. And it asks, what is the graph of y equals x squared minus 1 translated up 5 units? So ideally what we would do is we would take each of these values and shift it up 5, or shift up each y value 5 units to get our new points. And so then we would graph those. So this point should be negative 2, 8. This would be negative 1, 5. This would be, oops, put that in the wrong spot. Negative 1, 5. This one would be 0, 4. This would be 1, 5. And then we've got 2, 8. So this would be our graph if we shifted it up 5 units. If we wanted to, we could write the equation for this fairly simply. We should recognize that if we're shifting this particular expression up 5 units, it just becomes y equals x squared plus 4. We're adding 5 to that last piece to cancel out the translation there down by 1 that they had originally. So now that we have an idea how this looks, this should go a little bit quicker. So the first question says, how are the functions y equals 2x and y equals 2x minus 3 related? Well, we should recognize right off the bat that this minus 3 here means that it's the functions that are outputs. Oops. Our outputs are decreased by 3, decreased by 3. And so from a graphical standpoint, I don't even need to graph this to know what's going to happen. I should know their graphs are related, but I know that the y equals 2x minus 3 is translated down 3 units. And so if I wanted to, I could graph these. So let's go ahead and graph these. I'll get this off of here. And so I'm going to graph the original in red. So here we've got a graph. And then for our other line, we'll graph this one in blue. And we should notice that this graph has just been shifted down or translated down 3 units. All right, next. What is the graph of y equals 3x translated up 2 units? All right, so this is easy. We can start, if we want to, we can go ahead and graph this original graph, or if we're translated up 2 units, we know that that's going to go from y equals 3x, and we want to go up 2 units, so we're going to add 2. So we're looking to graph this equation. So we start at 2, we're going to go up 3, right 1. And there's our graph. If you want, you can graph the original to compare it. So it scrolls right through there, scrolling right through there, there we go. And it's just shifted up 2 quick units. All right, now we need to talk about horizontal translation. So for this first problem, it says the graph shows the projected altitude f of x of an airplane scheduled to depart an airport at noon. If the plane leaves 2 hours late, what function represents this translation? So if the original expression was f of x represents the actual time you're leaving, so the f represents the time that you're supposed to depart, and we're saying that we're going to delay it 2 hours. Well, the actual representation for the function that represents this transformation means we have to delay our time, or in this case our input, 2 hours. So f of x minus 2. And so if we look at this graph here, we should notice that the f of x is in black, and then the new flight time here would be in blue. What you have to start recognizing now is that a subtraction inside or applying to your input, or your x in this case, is actually going to shift it to the right. It seems kind of counterintuitive because when we were dealing with the vertical, subtracting dropped it down like it was supposed to, adding brought it up. But in this case, when it's inside and applying to the input, subtraction actually moves it to the right. Addition here would move it to the left. And here it says, suppose the flight leaves 30 minutes early. What function represents this transformation? So if we are talking about the original and we want to show 30 minutes earlier, but remember this is done in hours, so 30 minutes equals a half an hour. So if we're leaving 30 minutes earlier, we're going to be adding 30 minutes to our time here, so since we're leaving early. And so it'd be f of x plus 2. Should be f of x plus 1/2. I think I may have said f of x plus 2, but it should be plus 1/2. All right, so now we're going to talk about a reflection. A reflection flips the graph of a function across a line, such as the x or y axis. Each point on the graph of the reflected function is the same distance from the line of reflection as it is its corresponding point on the graph of the original function. When you reflect a graph in the y-axis, the x values change signs and the y values stay the same. Okay, so that's important, so make sure you star that. When you reflect a graph across the x-axis, the x values stay the same and the y value change signs. So when you have a function such as f of x, the reflection in the y-axis can be denoted by f of negative x, meaning that your x values change. And then a reflection in the x-axis would be negative f of x because the x stays the same, but the output, in this case, f of x, changes. So let g of x be the reflection of f of x equals 3x plus 3 in the y-axis. What is a function rule for g of x? So this time we need to denote some key information. They said the y-axis, so that means our y values are going to stay the same and our x values are going to change sign. Or if you remember from previously, so we know that when you reflect over the y-axis, you're really going from f of x to f of negative x. So that means in this case, g of x should equal f of negative x. So what this means is we're looking for g of x. We already know f of x equals 3x plus 3, but we need to make our input or our x value negative. So that means we're going to write it as 3 times negative x plus 3 because we're changing the x value since we're reflecting over the y-axis. So in reality, the function g of x is just negative 3x plus 3 when we simplify it. You could graph this and take a look at both of the equations, the original one and our new one, and you should see they are a reflection of one another. All right, let h of x be a reflection of f of x equals 3x plus 3 in the x-axis. So we're reflecting over the x-axis this time. What is the function rule for h of x? So if we're going over the x-axis, remember this means that f of x would change from f of x to negative f of x, or our output or our y values are changing. So that means in this case, h of x is equal to negative f of x. So if we're going to go ahead and calculate this function, we're going to have h of x equals, well, what's our f of x expression? 3x plus 3. So we have h of x equals, and this time we need to take the 3x plus 3, and we're going to change the entire thing, or we're going to change the sign by putting a negative outside of the entire thing, instead of just the x's in this case. Because we need to change all of f of x because this is what it represents. So in this case, when we're going over the x-axis, we're changing everything. So when we simplify this down, h of x would equal negative 3x minus 3. And a good habit to have here if you're reflecting something like this, go ahead and graph this. This is a quick graph. Compare it and make sure it is a reflection of what you started with. A vertical stretch multiplies all y values by a function by the same factor greater than 1. A vertical compression reduces all y values of a function by the same factor between 0 and 1. So basically, a vertical stretch means you're multiplying by something greater than 1, maybe 2, 3, so on. A vertical compression means you're multiplying by something such as a fraction that is less than 1 or a decimal. So the table at the right represents the function f of x. What are the corresponding values of g of x and possible graphs of the transformation g of x equals 3 times f of x? So basically we're getting that g of x is a vertical stretch by a factor of 3 of f of x. So to figure out what g of x would be here, its values, we merely just need to multiply f of x's values by, oops, not 6, 3, there we go, to find our new values. So in this case, instead of 2, g of x has a value at 6, and then a 6, negative 9, 1, or sorry, not 1, 3, and then negative 6. All right, I'm going to go ahead and graph f of x in blue, and then we'll graph g of x in red to see the difference. So f of x we're going to graph in blue. So we've got negative 5, 2, negative 2, 2, zero, negative 3, 3, 1, and 5, negative 2. Go ahead and connect these. And so that's f of x. Now we're going to go ahead and graph g of x in red so we can see the stretch. So g of x would be negative 5, 6, negative 2, 6, 0, negative 3, or 0, negative 9, 3, 3, and 5, negative 6. And so this is a vertical stretch. And there we go. So here it says, for the function f of x shown, what are the corresponding table and graph for the translation of h of x equals 1/3 f of x? So we're looking for a shrink in this case by 1/3. So we're going to try to find the values of h of x to finish the table. So we're taking each of the f of x values and multiplying by 1/3. So that'd be 2/3 here, 2/3 here. This would be negative 1. This would be 1/3, and this would be negative 2/3. Then we just want to graph both of these to compare the shrink. So I'm going to go ahead and graph. This time I'll graph f of x in red, or sorry, black. I'm going to graph f of x in black. So I've got f of x graphed in black, and now I'm going to go ahead and graph h of x in blue. And there we have h of x in blue. So we can see the shrink, the compression here. This is just good information here to help you keep track of how each of the various transformations takes place in regards to your parent function. Look it over, maybe add it to your notebook, but let's keep on going. All right, it says combining transformations. The graph of g of x is the graph of f of x compressed vertically by a factor of 1/2 and then reflected in the y-axis. What is the function rule of g of x? So let's just take this piece by piece. It says compressed vertically by a factor of 1/2. All right, so in this case, we know f of x is 4x, so we're going to take 4x and we're going to compress it by a factor of 1/2, which is going to be 1/2 times 4x, which gives us 2x. So there is our compression by 1/2. Then it says it's reflected over the y-axis. And remember, when we reflect over the y-axis, we're going to go from f of x to f of negative x. So we've got to change the x value. So in this case, to do the last part, we're going to go and we're going to take 2 times negative x, and then we just need to simplify this, which becomes negative 2x. So what happens is this is our g of x value. So g of x, or g of x function, is equal to negative 2x. So we just applied each transformation separately until we can combine them to create our new function. Question B then asks, what transformations change the graph of f of x to the graph of g of x? So they want to know, how was this changed? So let's just start by looking at g of x, and then keep in mind what f of x is. Well, f of x is 2x squared. I can turn this back into 2x squared if I factor out a 3. Well, now if I put this back into kind of a function notation, I've got 3 times f of x minus 1. It says what transformation changes or change the graph. So 1, we know we have a vertical stretch, and then the other being a translation down. So the two changes would be a vertical stretch by 3 and a translation down by 1. All right, same thing here, or very similar. Let's go ahead and take a look at these two. So for A, the graph of g of x is the graph of f of x equals x, stretched vertically by a factor of 2 and translated down 3 units. So for A, we're going to go ahead and start with our f of x value is just x, and we want to, in this case, vertically stretch by a factor of 2, so that means we would multiply this by 2. So that becomes 2x. Then translate it down by 3. So to translate down by 3, we would be looking at subtracting 3. So that means that our g of x function is going to be 2x minus 3. And then for B, we want to know how we go from f of x equals x squared to x plus 4 squared minus 2, or what changes do we see here? So we've got x plus 4 squared minus 2. Maybe I want to write the g of x in front of it. So this goes back to our rules for translations and various transformations. We know that this here is a translation down by 2. That's good. But notice here that we went from, originally it was x squared to x plus 4 squared. So that means that that 4 is inside impacting the input or the x value. So this is going to be a horizontal shift. And you have to think about it. We talked about this before. Subtraction moves it to the right, addition moves it to the left. So this is a horizontal shift left by 4.